In this presentation, we will identify the basic DeviceNet network structure, understand the role of the CAN protocol in DeviceNet network, examine frame priority, message states, and I/O types. Look at the application layer. DeviceNet is a communications protocol developed to eliminate the need for ever more complex wiring associated with the increasing automation of industrial processes. It replaced the single-loop electrical signal for each device with a single cable to communicate digitally with each device and provide power. Typically, this configuration consists of a trunk line out to the field with drop lines to each device. DeviceNet has open network architecture, which allows products from different vendors to communicate and work together. Open architecture means a network with a common protocol and software interface. This means users can easily add incremental devices to an existing or planned installation. Any DeviceNet product can plug into any network, so users can choose the best devices for their system. A single network interface can now communicate with all devices, sensors, and actuators, and all devices are interchangeable. DeviceNet is able to work with either a programmable logic controller, PLC, or an industrial personal computer, IPC, as the controller. The scanner card physically connects to the DeviceNet cable to the computer or a PLC. Each computer can have as many scanner cards as it has slots available. Each card is a separate DeviceNet network. The DeviceNet physical layer has a bus topology with trunk and drop lines. The shorter the network, the faster DeviceNet can communicate. At the maximum length of 500 meters, it will run at 125 kilobits per second. A maximum of 64 devices from 0 to 63 can be connected to the network, although 63 is generally used for commission purposes. Devices can be connected directly to the trunk line, as in multi-drop, so long as they can be removed without breaking the trunk line. A tap is a junction on the trunk line that allows drop lines to be taken from it for a cluster of devices. This can be as a star, a branch, or a tree. A branch line can be no more than 6 meters long. Terminating resistors of at least 120 ohms need to be placed on each end of the trunk line to minimize reflections and noise on the line. DeviceNet cable contains 5 wires, 2 twisted pairs, blue and white for data and red and black for power, and a drain which is bare. The individual wires are insulated and the data and power are shielded from each other. All wires are then surrounded with a braided shield. Cable comes in both thick 12mm and thin 7mm round varieties and in flat cable, all of which can be used for trunk cable. The maximum length of the trunk line depends on the speed required. The rate of communication is measured in the number of bits, counted in thousands per second, kilobits per second. 3 different data transfer speeds, known as the baud rate, are selectable: 125, 250, and 500 kilobits per second. As the device is optically isolated, communication power and device power can share the same cable. DeviceNet data link layer is defined by the CAN specification, which uses the CAN medium access control, MAC, and the logical link control, LLC, sublayer. Like Ethernet, CAN sends frames out over the network and uses a type of collision detection to determine priority on the network. CAN frames are much smaller and simpler than Ethernet frames, with the data section being 8 bytes long. CAN was developed in the mid-1980s as a way of reducing the wiring complexity in your average car. Up until then, each device was individually wired to the controller, resulting in a massive wiring which became incredibly complex. With CAN, each sensor is given a microprocessor chip and then communicates with a single cable which also carries the power, up to 24 volts. CAN also has the added functionality of managing which messages have priority and how to check for and isolate errors to protect the overall system. Every intelligent device on the network contains a CAN chip. The CAN chip is the brains of the component. It's the CAN chip that makes different devices from different manufacturers speak a common language. DeviceNet uses CAN frames for exchanging data on the network. The CAN protocol describes the operation of the data link layer. This layer describes the different types of frames and the error detection method. CAN network data is transmitted by means of a data frame. This frame type is composed mainly of an 11-bit identifier arbitration field and by a data field that may contain up to 8 bytes of data. The combination of identifier and RTR bit determine the frame priority on the network. There is also an extended data frame type with a 29-bit identifier field, and the devices will need to be configured to accept the correct size frame. Devices that only accept standard frames will not accept extended frames, and devices that accept extended frames will also accept standard frames. Frame priority occurs in a particular order. The start frame bit is sent out to synchronize all receivers on the network. The CAN identifier and the RTR bit combine to set priority. A logical value 0 is dominant and a logical value 1 is recessive, so dominant bits overrule recessive. If a station, while transmitting a recessive bit, detects a dominant bit on the network, it gives way to the higher priority and stops the transmission. The station that failed to send will attempt again at the end of the current transmission. The 11-bit identifier field contains the information necessary to classify the frames. This includes a message ID and the MAC ID, which, depending on the message group, can be either the source or destination MAC ID. A station wishing to send on the network the data associated with an identifier simply transmits the relevant frames. Besides the data frame, there is also the remote frame, RTR frame. This type of frame does not have a data field, but only an identifier. It works as a request so that another network device transmits the desired data frame. The CAN specification defines the error control mechanism, which makes the network very reliable with a very low undetected error rate. Every network device must be able to identify the occurrence of these errors and inform the other devices that an error has been detected. Every network device has internal counters that are incremented every time a transmission or reception error is detected and are decremented every time a transmission is successfully transmitted or received. If a significant amount of errors occur, the device can display the following states. Warning: when the counter reaches a defined limit, this means the occurrence of a high error rate. Error passive: when the value exceeds a higher limit, the device stops acting in the network when it detects another device in the network sending a frame with an error. Bus off: the device will not send or receive frames anymore. Frame creation and error detection alone are not enough for a network to operate. DeviceNet is the specification that indicates how the data is assembled and exchanged between devices. The DeviceNet application layer defines the services that are supported by the network, such as read and write commands, program management functions, addressing, uploading and downloading of data and virtual images. It is not concerned with the actual services, but more with their presentation to the user and programming of the network. DeviceNet uses the Common Industrial Protocol, CIP, in the application layer, which is an object-oriented protocol. The CIP has two main purposes: the transport of data to and from devices, the transport of configuration data and diagnostic information of the system being controlled. The software that organises and controls the network may be a Windows-based program and could use a flowchart code, ladder logic, or any other control language. This configuration software is required to assign each component an address. Software can be used to display the system on a screen where the system can be monitored and changes can be made. This is called an HMI, or human-machine interface. Every DeviceNet device has a configuration file, also known as an EDS, electronic datasheet file. This file contains information about the device operation and needs to be registered in the network configuration software. The user will get access to the equipment parameter list, which can be accessed through explicit languages. Also in the network configuration software, a method of I/O data exchange will be chosen, i.e. polled, change of state or cyclic. DeviceNet protocol has two basic types of messages, I/O and explicit. Each one represents a specific type of data. I/O messages move data according to priority between one or more devices. These messages have four different methods of exchange. Polled is a communication method where the master sends one telegram to each of the slaves of its scan list. As soon as receiving the request, the device responds promptly to the request from the master. This process is repeated until all are consulted, restarting the cycle. Bit strobe is a communication method where the master sends over the network a message containing 8 data bytes. Each bit from those 8 bytes represents a device that, if addressed, responds according to the master. Change of state is a communication method where the data exchange between master and slave occurs only when changes in the monitored controlled values happens, until a certain time limit. When this limit is reached, the transmission and reception will occur even if there were no changes. The configuration of this time variable is done in the network configuration program. Cyclic is another communication method very similar to the previous one. The only difference is in the creation and use of messages. In this type, every data exchange occurs at regular time intervals, whether or not they have been changed. This time period is also adjusted in the network configuration software. DeviceNet requires a connection to be established before data can be exchanged between devices. Each DeviceNet node needs to use the Unconnected Message Manager, UCMM, which uses explicit message types to establish a connection, which will then be used for process data exchange on the network. Explicit messages are a kind of general-purpose message without priority, which are mainly used for setting parameters and configuration of devices. A DeviceNet node can be a client, a server, or both, and a client or server can produce or consume messages. A typical node will do both, but the protocol allows several communication possibilities among the devices. The protocol can also detect nodes with duplicate addresses, MAC IDs. Avoiding duplicate addresses is more efficient than trying to locate them later. DeviceNet is primarily a point-to-point message model using a simplified I/O message type, very common in control applications. The advantage of this is that devices with limited resources, like an 8-bit processor, can run the protocol. DeviceNet has an open architecture, which means that any DeviceNet product can plug into any DeviceNet network and have a common software interface and configuration. A single network can have 63 nodes up to 500 meters long with data and power in one cable. Every DeviceNet product has a CAN chip which communicates using CAN frames at the data link layer. These can be 11-bit standard or 29-bit extended frames. CAN determines frame priority on the network with the dominant logical 0 gaining priority over logical 1 on the network. Error frames are counted and recorded by each device, which will remove the device from the network over a defined limit. Every device has a configuration file known as an EDS file to configure the device on the network. I/O messages are used for process data and explicit messages are used for configuration. There are many possible connection configurations available between devices to suit various tasks.